same on them. We always have an object that we've got set up. Object, object. We put a plate of glass in between us and the object called a plane of projection. Plate of glass, plate of glass. This is what we're drawing on. The only real difference is where the reader is defined at. On orthographic projection, like in this figure, you are set at infinity. Therefore, these rays of projection, remember I talked about laser beams coming out of your eye and etching on that glass? Well, you're so far back that they come out parallel. Therefore, the object appears true size and shape. When we do pictorial projection like here, we define your location. Therefore, your line of sight is not parallel, and the object appears more realistic or real life. It's not true size and shape, though. Therefore, we can't really scale on them. We can't dimension them effectively because our drawing doesn't really have the right sizes on it. It sees it as our eye sees it. But in essence, this is the difference right here, where you're defining the reader or the drawer. Okay? That's the difference between the two projection theories. Everything else is pretty much the same. To kind of compound on that, let's go back to chapter 12 and look at figure 12.3. Where here we looked at this one yesterday with Durer. This shows that same setup, but instead of a drawing, you see a physical practice of that theory. Okay. So here we have a subject or an object. Here we have a plate of glass that sits in between us. Here we're defining the location of the reader. Therefore, your lines of sight as they come out, they're kind of expanding out to the outside. We etch our figure on here. If I was doing orthographic projection, Durer would not be in this picture. He would be way, way, way off there, right? So that our lines of sight were parallel. All right, a couple other terms as far as perspective drawings go. Can anybody recall what a horizon line is and what it represents? HL. Declan, want to weigh in on that? Or you just scratching the back of your head?
The horizon lines, like where in this picture it meets the sky. There.
Okay.
Where the vanishing point could be.
Yes. Okay, so two things on the horizon line. It represents the curvature of the Earth, or where your line of sight leaves the Earth. And that's a great picture that Declan showed. He looked at figure 12.1. You can see the horizon line where the railroad tracks look like they disappear. Your vanishing points reside on that horizon line, unless we're doing a three-point perspective. What's the ground line represent? GL. Does anybody know that one?
Where the object sits on
Yes.
the ground line?
Represents the surface of the Earth. Okay, where the object sits. Now, we don't really see that in the resulting view. Like here, let's go to the railroad track. Because this is very similar to the one right across the page, figure 12.4, where they're looking at the road setup. Okay, the ground line's somewhere sitting in here when we draw this. We don't really know where it's at, but it's how we take everything and put it on the surface of the Earth. Okay? And you'll see how this works today. We're going to actually do a few perspectives, depending on how much time we have, what we get done. But the ground line represents the surface of the Earth, not the curvature of the Earth, the surface of the Earth. Everything sits on it. Well, I guess I shouldn't say everything. Maybe we're drawing an airplane. In that case, we'd still use it to locate, the ground line would locate where it's at in the sky. So it controls our elevation. All right, the easy one of those three planes, the picture plane, or PP. What does that represent? Picture plane. Yes, Jess?
Plane of glass that we project.
represents that plate of glass that sits between us and the object. Okay? We had a couple other terms. Station point. What did station point represent? Yes, Sean?
That's where the, like where the reader would be viewing from, or the drawer.
Yep. Okay, it's the defined location of the reader. Remember, in orthographic projection, we never did locate a station point because you're at infinity. If we're going to do perspective drawings, we need to locate that point. We're defining that location. Vanishing points, what are those? VPs.
Where your line ran to.
Okay, I think all of you are kind of doing this stuff. It's where your planes vanish to. They usually reside on the horizon line. And for the purposes of our drawings, they always will reside on the horizon line. And these are just your vanishing planes. Were there any other of those terms right at the start of the chapter that you might have had questions on, such as your line of sight, any of those? Okay, let's go to page 637.
I do have a question.
Yeah,
So
sure.
when you go into the 3 point or 2 point, is there a defined set where those are coming from, and these angled spaces? You know, is it 3 point, you can't just go 1, 2, 3 over here. Is there a defined, is there a logic or reason where they go?
Yes, there is. There is logic and reason. They are a variable that is controlled by the horizon line and the station point. And you'll look at how we set these up when we start drawing. Okay. But basically, you pick how you're going to look at an object, and then that defines where these horizon lines are. Okay. We don't have an example of a 3-point perspective in our text, but we can Google it pretty quickly. Wow, this is
That's what I'm saying, who picked those, and where, you know,
Yeah.
they go 1, 2, 3. Okay.
All right, so we've got 3 perspectives here. These are the 3 different types. And let's go over the characteristics of each. Let's start with the first one. This is a 1-point perspective. When it says 1 point, we have one plane that vanishes to a vanishing point on the horizon line. This is not considered pictorial projection. This is actually considered orthographic projection. And you're going to see why when we draw it. In essence, this first side right here is true size and shape. Then this receding plane, the depth plane on here, is the only one that vanishes. Therefore, the majority of the object is drawn with orthographic projection, and it's true size and shape. So that's what they consider. This is pretty much the exact same technique as an oblique drawing, except that we vanish that receding axis to a point. On an oblique drawing, the vanishing sides are parallel. That's the only difference between the two. This one appears a little more eye-pleasing. So orthographic projection, one plane vanishes. This drawing right here has the most distortion out of all of them. It's not really done a lot in industry unless you're sketchy. Then some people will do it. The next one's 2-point perspective. Far and away the most widely used concept. On this one, we have 2 planes. So our Y plane, it doesn't vanish, but our X and Z planes do vanish. You have 2 vanishing points on this one. So to compare and contrast, on this one, the front side's true size and shape. On this one line on the object will be true size and shape. And that's probably it. Just one line. We also rotate the object a little bit on this one. We'll go over the setup a bit later. This one really looks so eye-pleasing that people really can't tell the difference between this one and this one unless they really, really study them. So the one that's used in industry right here. The one we're going to really focus on. The 3-point perspective, all 3 planes vanish. Okay, so we've got still width, and depth vanishing to the horizon line. Now we're taking elevation or height and vanishing it down to this point. Obviously, the most realistic of all of them. You will start seeing these. I mentioned this the other day. Now that we do 3D solid modeling as a pretty common occurrence, computers can generate those views in seconds. It would take us a substantial amount of time to produce those views on a CAD system or by hand. So, you're seeing this guy come back. This 2-point and 3-point are considered pictorial projection. So we're using those pictorial techniques. Now we have some variables that go on when you set these things up. And it depends on what your view that you want as a result. Now, I will tell you, the book gives you some guidelines, but in essence, it really kind of takes some experience in doing them. And saying, oh, I looked at it this way last time and I got this type of result. So I don't like it. So I'm going to transpose that to the next one. So there's quite a bit of experience that goes with these. But the guidelines the author gives you will get you started in the right direction. Folks, if you get to be good at this stuff, there is jobs where this is all you do. I know several people that this is all they do is perspective drawings and pictorial views. I know there's a guy in Boise, I don't know him personally, met him once, but I've seen his work. All he does, people send him models, and he does pictorial views. I know the first ed, when they built this one by Cheney, they paid him 12 grand for one drawing. And he did it as a freelance. What he did is he went in and did the 2-point perspective and sketched lines, printed onto a canvas, took it off, and he paints with oils and made it look realistic. Put cars in it, people in it, that type of stuff. And he runs his own business, and that's all he does. There are other firms where people get good at this and express a desire to do it, and that's their job in the firm. And these are firms that are larger, where they have certain drafters designed for certain tasks. So if you like doing this artistic stuff, and you get good at it, you might turn it into a career someday. Now, for the most part, most of us drafters don't do this stuff. I never did a single one when I was. Miners, we don't care. Blow it up, haul it off. Okay, that's about it. But there are other industries that did, yeah. When we build our plants and stuff, then we would have perspectives and those types of views. All right, let's look at some of the variables. The first one is the relationship to the horizon line to the ground line. And I'm going to go to page 636, right across the page from where we're at, figure 12A. How you control elevation in a perspective drawing is where you put the horizon line in relationship to the ground line. Okay, that controls your elevation. Whenever you have the horizon line that sits above the ground line, like they show in all the examples in the text, we call that a bird's eye view. Okay. Basically, your eye is going to sit somewhere above the ground. Okay. Your planes will vanish above the ground. That's a bird's eye view. When we take that, we do a bird's eye view and we set the horizon line exactly 6 feet above the ground line, we call that a human's eye view. Now, you don't have to set it at 6 feet, but that's just kind of a good, easy, generic number for the human species, right? Yeah. But you could set it at you are 5'3", and said, I want to do that, or you're 7'6", you could set it there. Okay, whatever the case might be, but that would control where it looks like you're looking. So if I'm doing a house in our perspective drawing, it's going to look like I'm standing in the street looking at it because you're going to see the same stuff most people will see with their eyeball. Ground's eye view. The horizon line and the ground line sit on top of each other. This is like you're laying on the ground looking at something. Nice summer day, you're out in the grass studying. Out here in the front lawn, you lay down, take a little nap because you got halfway through chapter 14, put you to sleep. You wake up and you look at the building. That's the view you're going to get. So it's like you're sitting on the ground. Last one, put the horizon line below the ground line. We call it a worm's eye view. because now you are underneath the structure. Okay, so we've got these views, bird's eye, which is really a humans and bird's eye, anytime the horizon line's above it. You got your ground eye, you got your worm view. Why would we choose one of these? What do you want to display on your drawing? Yes?
So like if you'd go to the Twin Falls Canyon and you're standing at the ledge, you could project the bottom of the canyon, then you can project the top and the buildings, right? Is that kind of like it?
Yeah, you can see the bottom.
Yeah, you can see like some of the canyon and then some of the buildings. Oh.
Yeah, it basically, what do we want to display in the drawing? Do you want to see the top of the structure? Do you want to look into the middle of it? Do you want to show the bottom of it? Is there some important detail down there you need to see? Okay, so in essence, it's what do you want to display in the drawing? That's what's going to give you. You're going to look at the top, you're going to look at the middle, you're going to look underneath it. Okay. So that controls your height, these variables. The relationship of the horizon line to the ground line. Now, that controls height. How do we control left and right? If you look at every one of these examples, they're showing pretty much the right side of the object. Well, how are they controlling that? You do that with the station point. So let's go to figure 1211. The author recommends this distance from the object, where you take your station point, you draw lines to the extent of the object, here and here, because this is your eyeball, right? Okay, so when I'm looking from this location, I'm going to see that edge and that edge. And they say move this up and down until you get approximately a 30-degree cone of vision. And this has turned out pretty good. Now, does it matter if I'm 29 or 31? No, not really. Do I want the object to appear a little more distant? Then I would probably make that a narrower one. It's going to push my station point away from it. If I want to appear like I'm closer to the object, then I would make that shorter, 15 degrees. That pushes the station point up, or excuse me, 60 degrees would push the station point up, right? Closer to it. This is a real good place to start. Okay? So a 30-degree cone of vision. Now, on this one, they're looking right in here. What if I wanted to see more of this side than this side? All I would do at that point is I would start moving my station point, like maybe over to here. I'm still going to do that 30-degree cone of vision. So I'm going to draw a line then from there to there, and I'm going to try and get 30 degrees in here, or approximately. Now, by moving over here, you can see now I get very little of this side. It's going to appear very skinny. I'm going to see this side almost orthographically, because I'm looking right into this corner. I'm going to see a lot of that, I'm going to see a lot of that. I won't see the back of this at all. This is also telling you what you're going to see. Okay, so start with your 30-degree cone of vision, and then swing it left or right. If I wanted to look at this side of the object, I would move my station point over to here, use my 30-degree cone of vision, and that's what I'm going to now see. Okay. So we just move that station point around for the definition of where our eyeball sits in relationship to my object. You kind of see this on the next page, page 639, on the one-point perspective. So this is a setup for a one-point perspective. Now, what you're looking at here on this is a piece of paper. What you're looking at is a bird's eye view. So you see the ground line. That's a plane, right? And it sits here on edge. That line is the ground line like such. You see the horizon line right here on edge. It's a plane. You're seeing it on edge. Here's your picture plane up here. Again, you're seeing it as a line because it's a plane on edge. Now, what we then do is we take some view that has height on it. That's this view. It could be a front, right, left side view. These are orthographic views. Any view that has height, or the y-axis, right? Does the front view have height on it? Yeah, does the right side? Yeah, either one of those views would work. That's the only dimension we're looking for. They notice they set it where? Right on the ground line. Okay, so they're defining this object is going to sit on the ground. Okay. This view. Okay. This one gives you width and depth. It must be one of those views. Typically, you're going to use a top view here because you have width and depth defined. Again, this is an orthographic view. Now, when they set it up, notice that this is a top view. This edge right here sits right on the picture plane. That edge is what? The front side, right? Now, on a 1 point, what does that do for you? And let me kind of try and illustrate this. So here's my picture plane. Now remember, you're defining this thing. And we're going to put an object somewhere back here. So it's in here. Let's see, is that kind of, let me put a white piece of paper. So you can kind of see this without that text. Okay, so I've got this. Now, if I have my object back here, remember, you're defining the location of the reader, so all of you are using your eyeballs, that's the location. If I put the object back here, is my drawing on my picture plane going to be smaller, true size, or larger than the actual object? What is it going to be? It'll be smaller. Okay? And I don't know if you can see that through that piece of element. But it's going to be smaller, right? Because you guys are looking through here, and the object's sitting back here, so those rays are going like this, right? Because your eyes are going, nobody in here only has one eye. Okay, so you're going like this, right? If I put the thing in front, is my drawing going to be larger, true size, or smaller? Be larger. Now, what if I take, here's my front view, and I'm going to take it and set it right on the picture plane. It's exactly true size, right? Yeah. Okay. Isn't that what's going on this figure? They put that front edge exactly on the picture plane. So in essence, that front edge is going to be true size and shape. That's why this is considered orthographic projection. So when I come to draw this down here, and they get this view, I'll go right here, that's true size and shape, that's orthographic projection. All I have to do to draw that is take these lines, take them straight down, bring these over, right? Laws of orthographic projection, rule 1. You can project perpendicular in any adjacent view. And you build it. Now that works for any plane touching the picture plane. And I want you to really think about that. At any point of the object that touches that picture plane, it must be true size. Okay, and that's how you, in essence, that same concept is how you build or change elevations on a 1 point, 2 point, and 3 point. It's the only way to build the object. Whenever you change elevation, you have got to get to this picture plane. You've got to get there. Okay, so we set it up as such. Then next thing we do, we locate the station point. Do I want to look at the right of it? Do I want to look right into the object? Do I want to look at the left of it? 30-degree cone of vision. So you're picking this up. You're setting this on the ground line, you're setting this on the picture plane for 1 point, and then I decide, oh, I want to look at the right side. Then my station point would be over here. I want to look at the front of it. I would move it right down here in the middle. If I want to look at the left of it, I'm going to move it over here. Those are the variables that you use when you set it up. After that, it is all projection theory to produce the drawing. Let's go to page 642.
Wait, can you back up real quick?
Yes.
Back it up. So then your vanishing point is perpendicular to the staging point?
Yeah, I didn't go over how to do the vanishing point, and I probably should have.
Yeah.
So, okay, so we're using orthographic projection for everything touching the picture plane of the front view, right? How do we get the back plane, or this stuff back here? We have to get the vanishing point of the depth axis. On a 1-point perspective, all you do is come to the station point, you follow the angle of your vanishing plane. So here's my depth axis. Which way does it go? It's vertical, right? Okay. So in essence, what we really do is we go from the station point at the angle of my depth axis, which in this case is vertical. You go up to the picture plane and back down. They only show it going here because it's a vertical line. Where it hits the horizon line is where that vanishing point hits. It's a little confusing on this because the author's view isn't great. It really becomes apparent when we look at the 2-point perspective. So just take it at the same angle as your depth axis to the horizon line on a 1-point. And Lisa, I think this will become apparent when we do a 2-point, and that's where we're going right now. Okay, so page 642. Now, they give you 2 examples of a 2-point perspective on page 642 and 643. Stick with the ones that say plan view method. Okay, the one on 642 is the plan view method. It pretty much matches orthographic projection. Okay, so you're already used to that. The measuring line method works also on the next page, but in my mind, why know 2 ways of doing it? Okay, so I'm going to start with step 3 on here. Okay, ground line, horizon line, picture plane. Is it a worm's eye view? Is it a human's eye view, ground line view, or bird's eye view?
Can be human.
Human.
Well, we don't know the distance.
Yeah.
Yeah.